So let's jump to the third exercise, which is about one of many possible proofs for the famous Pythagoras theorem, which you all know in the most common form, that a squared plus b squared equals z squared in a rectangular triangle, in any rectangular triangle, where of course C must be the hypotenuse, which is always the longest of the three sides of a triangle. And now, how to do this using vectors? You see here that A, B, C have been chosen so that the vectorial sum of A plus B equals vector C. So that's a good hint at what we have to write down. We should first list all the facts as equations and then formulate the theorem in vectorial notation in order to prove it. So my symbolism is as follows. This triangle symbol denotes that I build or I construct a vector sum of A plus B equals C. That's all. Okay, so that's already one vector equation using vector addition to show what we have, or just to write down what we have. The second one is more important even, or a little more special, and it's obvious that due to this right angle, which is a very important feature of this triangle, you remember that two vectors which are perpendicular to each other always have a scalar product of 0. Okay, this is the symbolism for A perpendicular to B. Okay, so definitely, since the scalar product includes something like the component of one of these vectors in the direction of the other, we can see that the component of vector A, for example, in the direction of vector B is 0. And so the whole thing must get 0. It's nice to write down A scalar product with B equals 0. Some of you may be used to use a symbol like this one for scalar product, but this is not necessary. You can also use the simple multiplication sign. This is what we do. So that's it. We've got two equations. And now let's formulate the theorem, which is to be proven in vectorial form. The best way to do it is to say that the absolute square, I wanted to say the squared absolute value of vector A. You know what I mean? I take the absolute value of vector A, which is nothing else than the length of this vector, okay? And then I square it. So that's like what's usually written down as A squared, because with A we denote the length of the triangle side. And of course, this is the absolute value of this vector. So absolute value, let's call it the squared absolute value of A plus squared absolute value of B equals squared absolute value of vector C. That's Pythagoras theorem in vectorial form. Now, how do we prove it? Well, there's a nice way. There are not many alternatives actually. So I can do the following. From the first equation, I can try to eliminate in some way. So because A and B appear in both of these equations, it would be possible to isolate B in this equation and then fill it into this equation in order to eliminate it here. And that's what I'm doing, okay? So I reform this equation by isolating B. B vector is then equal to C vector minus A vector, subtracting by the rules of vector subtraction, of course. And then I fill this in instead of vector B at this place. And then I get A scalar product of, instead of B, I write C minus A in parentheses, still equals 0. Now it's important to know, I think in your script also listed are all the calculation rules or algebraic rules valid for scalar product and also for vector product. One of them is the distributive law. This kind of distributive law is valid for the combination of scalar product and vector subtraction, also for vector addition, of course. where vector subtraction is, in a certain sense, it's just a special case of vector addition. Okay, so distributing is nice here, is fine, because we may remove the parentheses. And it means now, where it tells us that the scalar product A times C vectors minus then A vector scalar product times itself, okay, A times A equals 0. And now that's nice to have, because this one appears in our theorem to be proven. We may all know, you should know, that this sometimes I call it the Eigen Product. So actually the scalar product of a vector by itself is always exactly the same thing as the squared absolute value of this vector. So actually this is the most elegant way to calculate the squared absolute value of a vector. Okay, so we have A times C, I just shortly speaking now, A times C minus A squared equals 0. And then you may see I can isolate a vector absolute value squared by, just isolating it, putting this to the other side, and then we get equals to A times C, A vector scalar product C vector. This I call equation number 3. Now I could, perhaps there would be an abbreviation from this point on, but if that has worked so fine, I could do exactly the same thing, isolating A, then eliminating, this time eliminating A from this equation, and this is what I've done here. From 1, I start out right again, okay? So A vector equals C vector minus B vector. It's the same procedure, but using different vectors, of course. But you see now what I get this time. I have A scalar product B, and A is replaced by C minus B. So now the parentheses are on the left side. Here it was on the right side. So I have C minus B times B equals 0. And then distributing again, using distributive law, C times B scalar product minus B times itself equals 0. This is again squared absolute value of vector B. And then isolating this, I get it is equal to C times B scalar product. That's nice, equation number 4, because now we can use our theorem to be proven by filling in this for A squared and this one for B squared in the Pythagoras theorem on the left side. And you see what we get. It is A scalar product C plus B scalar product C. And here we can again use the distributive law, but the other way around, by putting the factors A vector and B vector in parentheses and moving C vector outside of these parentheses. Okay, so this is the same as A plus B vector times C vector. In other words, if I distribute here, from here to there, it's obvious, okay? A times C plus B times C, so that's allowed what I'm doing here. And now I can use equation number 1 again, which says that A plus B equals C vector. I get C vector times itself as a scalar product. So this is the Eigen scalar product again, which results to the absolute value squared. Now we've constructively shown that this left side of our theorem is exactly equal to the right side. So that's a valid proof after all. I would be interested if any of you found another, perhaps more elegant or direct way to prove it. I think it's not necessarily the fastest way. If so, you can tell me. If not, I say goodbye.